Welcome back to For the Mariners by the Mariners channel. In the challenging environment of the open ocean, the design of a ship propeller is a feat of material science and precision engineering, where the choice of alloys can mean the difference between peak performance and catastrophic failure. The propeller hub serves as the central foundation that must withstand immense centrifugal forces and the pulsating torque of the engine shaft. For controllable pitch propellers, the hub design is even more complex, as it must house the hydraulic cylinders and mechanical linkages required to rotate the blades while remaining perfectly watertight. When selecting materials for both the hub and the blades, engineers look for a specific combination of high tensile strength, corrosion resistance, and resistance to cavitation erosion. The most common material used in modern maritime industry is nickel aluminum bronze, often referred to as Naval. This alloy is favored because it develops a protective oxide layer that resists the corrosive effects of salt water and provides exceptional fatigue strength, which is vital for components undergoing millions of stress cycles. Another popular choice is manganese bronze, which offers a high strength-to-weight ratio and is easier to cast and repair, though it may be more susceptible to stress corrosion cracking over long periods. For smaller or specialized vessels, stainless steel is often utilized, providing incredible durability and impact resistance against ice or debris, though its higher cost and weight must be carefully considered during the design phase. The design process also focuses heavily on the grain structure of the metal during the casting process, to ensure there are no internal voids or inclusions that could lead to crack propagation under the heavy load of the propeller thrust. Beyond traditional metals, the industry is exploring the use of carbon fiber composites for propeller blades. These composite materials offer the advantage of being significantly lighter than bronze and can be designed with a specific degree of aeroelasticity, allowing the blade to slightly change shape under different loads to optimize hydrodynamic efficiency and reduce underwater noise. However, the transition to composites requires careful engineering of the hub interface to manage the different thermal expansion rates between the metal hub and the synthetic blades. Surface finish is another critical design consideration, as even the smallest imperfection can trigger cavitation bubbles that eat away at the material surface over time. High-precision machining and robotic polishing are now standard practices to achieve the mirror-like finish required for modern high-speed propellers. By carefully balancing these material properties with the hydrodynamic requirements of the vessel designers, ensure that the propeller remains the most efficient and reliable link between the ship's engine and the sea. If you found this video helpful, please give us a thumbs up, hit the notification bell, comment, like, share, and subscribe for more insights. Thank you.